Yeah. All right. Let's get started. Got the lab done? So in your sleep. So when you woke up? Yeah. I solved this fantastic multivariable calculus integral one time in my sleep. It was great. Scribbled it all down, woke up the next morning, pure gibberish. But I slept well after that. Question. What's a good resistor value? I like 10K and 1K. Mega ohms are always nice. You know, if you get a long enough wire, it can act like a resistor. What's a good resistor value for the lab? That's a different question. I would recommend against a really big one. Mega ohms or hundreds of kilo ohms. Garrett, wasn't it you who emailed me and said you're seeing a significant attenuation of the signal going? Yeah, so you've got a voltage divider. Yeah. If you got a triangle wave coming out, what that's going to make you do, if you have a triangle wave coming out of your integrator, you're not integrating enough, and that will make your frequency do this. It'll speed up and slow down and speed up and slow down, and you'll get all kinds of oscillations. And it no worky. Another question. Bigger capacitor. Bigger capacitor. No other takers? You excited to do the next lab? The next lab departs significantly from this one. Because this lab epitomizes what you're not supposed to do when you're doing concurrency. Because we're dealing with concurrency in an interrupt service routine, which sometimes you need to do, but that approach doesn't scale because you normally have a lot of different tasks that have to run at different rates, and things fall apart to a significant degree once you've operated on trying to do concurrency and interrupts. You can make it work, but it's kind of a hack. So, starting with Lab 5, we're building an operating system to do it instead. I'm getting a couple of, we're doing what? Nobody stood up and said, all right. Okay, I promise it won't be too bad. It's really, really cool. Okay. All right. So if you remember what we were talking about last time, it was we're defining the context of a process so that we can talk about context switch. And so in order to figure out what the context of a process is, we have to figure out where does the program hold its state? How does it remember information? Because the places where it remembers stuff, if we mess that up somehow, when we freeze a process and restore it later on, if we mess up its state, it's going to mess up its functionality. Its values will all be messed up. Something won't work right, okay? So we have to isolate the state of one process from another process. In order to do this isolation, we have to figure out where is that state held. So we talked last time about how state can be held in the heap, it can be held in global variables, it can be held on the stack. The state can be information relating to the data on which the program operates, and it can be information relating to the control flow of the program. Like where is this so this process is executing a bunch of code. Well, it's in the middle of this subroutine. Where was it before that? Well, it's got a return address, and you got to as soon as that function returns, it's got to know where it's got to go back to. So you've got to save the call stack. Okay, so you've got this stack of return addresses and function calls, local variables, stack frames, all on the stack. So this is in general where variables are stored and where the control flow information is stored. There's also a couple other locations. So the immediate results of where things are stored in the processor, you're operating in registers, so state is held in registers. Likewise, when you're doing conditional evaluation, you store information in the condition codes, which is held in the status register, the CPSR. So we've got to deal with all of this. We already know how to how to deal with registers. We've seen when we're handling an interrupt, we push all the registers onto the stack, and the hardware automatically saves the CPSR, so we know how to save registers. How do we deal with the rest of it? So we started talking about whether or not is it necessary to isolate these aspects of a process's state from another process. And what I told you about last time is what we're really dealing with is we're not separating the address space of two different processes like you have on Windows. We're actually creating threads, where all these threads share the same address space. So we're going to allow them to share each other's global variables. So do processes share global variables? That depends on what we're trying to do. And for this class, for what we are trying to do, we're going to allow our processes to share global variables. So we don't need to isolate the global memory space of one process from another process. It's the same state. It's the same locations in memory. So we're going to allow global variables to be shared. Do we share program counters? No, we don't, because every process is doing its own thing. It's got its own trajectory in the code space, and so we have to make sure that we isolate and protect one process's program counter from another process's program counter. Do we share register values? We've also talked about that. That would be disastrous if we allowed two processes to share the same register values. They have to share the same registers because there's only one set of registers for the processes to execute on, but the values contained in those registers, if we pause this process and run that process, this process that is running will necessarily overwrite and destroy the values that are held in the registers that this process depends on. So we have to take a snapshot of the register file prior to doing any context switching. So they don't share registers. Do processes share the heap? Again, this depends on what you're trying to do. So we're going to allocate heap variables, and we're going to access those heap variables and maintain state information in those heap variables. What this boils down to is when two different processes call malloc, should they be, and they both grab data off of the heap, is that heap that they're grabbing data off of separate for each process or shared by all the processes? So under Windows, under Linux, modern 32-bit operating systems, each process has its own heap, and they interact with the operating system in order to do virtual memory mapping of pages from actual RAM into the heap. But for our operating system, for our real-time OS that we're building in here, we are going to allow processes to share the heap. Do processes share their heap allocated variables? Only if they want to. So a process grabs some heap memory, points a pointer to it, and operates on that structure that it allocated from the heap. There are times where you want to design your software so that different processes can access that same heap allocated structure, in which case you'd have to have like a global variable pointing to that heap allocated structure so that different processes can access it. But what we're doing is we're going to give that option to the programmer, and also that responsibility to the programmer to make sure that if they have a heap allocated structure, that if they want to keep it local to the process, that they don't somehow expose a handle to that to another process. And the way that they do that is you declare a local variable to be the pointer to the data that you allocate from the heap. So if we're using a local variable should be local to the process. If it's local to the process, that means another process can't get to it. But that yet compounds the problem yet again of how do we keep local variables local? How do we make sure that a process's local variables don't get whacked by another process? And so that brings us to the next one. Do processes share local variables? Well, that kind of violates the idea of a local variable. So we have to draw the line on local variables. Processes do not share local variables. How can we keep processes from whacking each other's local variables? Well, where are local variables allocated to? They are allocated to the stack. Okay, so let's suppose that two processes shared the same stack. Let's say we've got P1 and P2, and P1 is over here running through. It calls a function A, then B, then C, then A, then B, then C, and so forth. And P2 over here runs function N, then function N, and it runs in an infinite loop. And so let's suppose that we're just running a bunch of code. Let's say that during A's processing, it calls, during P1's processing, let's suppose it's calling function A, and function A has a bunch of other functions inside it like Q and R, and then let's suppose that in between, right after R, we decide we're going to freeze process A. So right here we're going to preempt process A. So we're going to freeze A, or process P1, which is running function A. So we're going to freeze this guy, and we're going to switch to P2. And P2 is in the middle of its loop where it's, let's suppose it was in between running P and Q. Okay. If we draw a stack frame for what's going on in P1, so at the time that we preempt, we've got a return address on the stack, we've got the frame pointer, the stack pointer is pointing to the frame pointer. We're going to preempt process 1. Okay, if P2 shares the same stack as P1, then we're going to load the context of P2 in, and then P2 will start running on this same stack. So it'll be in the middle of some function call, its stack pointer will be pointing over to here, and then we'll do something like a return. And so P2, instead of, so if we can see up here, P2 wants to return to function Q. P1 wants to return to function, so it's in the middle of this function between R and S, and it wants to return to A. So because of the fact that we're sharing, if we share the stacks, that return address is a return from A back to main. When we return from P2, we return to the wrong spot. Remember, P2 is executing its own little function chain, and we want it, when it returns, to return up P2's call stack. If we have them share stacks, it'll return up P1's call stack. That's what you call weird behavior, and you don't want that to happen. So if we have them share stacks, they're sharing the same call stack, and the return gets messed up. And not only that, but when we return, P2 starts executing in the context of P1. P2's local variables are P1's local variables. It's just all messed up. So how do we avoid this? The idea is we want every process to have its own stack. If every process has its own stack, all the local variables are pushed onto the process's stack, and that way we don't share anything between these two stacks. Okay, what then is the process's context? Two things: register values, the process stack. Again, so we had the debate about, or at least I was trying to engage you guys in thinking to have the debate about. You didn't debate me much. Whether or not the heap should be part of the context, whether or not the global variable should be part of the context, and I hope that you agree with me they shouldn't, but we do need to have the register values of a process and its own stack be part of that context. So if this is the process's context, how do we save that process's context? Well, what we need to do is take the context of the process, copy it to its own little memory location, and call everything good. So we need to copy all the contents of the register values and the contents of all the stack of the process off to some isolated memory location. That's our bank. That's what we're going to save. Okay? Wait a minute. Copy the entire stack. How deep can your stack be? Pretty darn deep. So they're telling me that we got to copy the entire stack off to some other location in memory. That's a lot of copying. Well, this is why we love pointers. Because we're not going to copy the entire stack. We're going to use the process's local stack as that holding location for the process's context. So we need to store the register values, and we need to save and store the stack. What we'll do is we'll just say, okay, this process's local stack, we're going to push all the registers onto its local stack. Then we'll point the stack pointer at a different stack. Excuse me. Okay, so context switching is the process, and we're using the overloaded term process there, of saving the context of one process and restoring the context of another process. So we're taking those aspects of hardware that hold on to the context of a process, and we take the contents of those hardware facilities, and we save them in memory. Then we reload from a different location in memory the context of a new process and put it into the hardware of the processor, and that will allow the processor to proceed to execute the context within the context of the new process. Okay. the only process that gets to access the CPU is the process whose context is active. Or in other words, whose context is the one that's currently executing. Okay. Questions we have to address. So now that we know what we have to do, we have to figure out how to do it. How do we take the context of a process and state it? And then when do we invoke the context switch? So how do we implement context switch? When do we invoke it? So if we answer the second question first, we have two options. Context switch can be invoked by a process. So this is where a process voluntarily swaps itself out. This is what we call a cooperative context switch. This is what you hope happens when you call like a yield function, where you want to wait for something else to happen, and so you just say, okay, swap me out and let somebody else do something because I'm just waiting. I don't need to be burning CPU cycles. Okay? Alternative to the cooperative context switch, your context switch can be invoked asynchronously or implicitly without requiring a process to directly invoke the context switch. This is called a preemptive context switch. So this is when a process is going along and all of a sudden the outside entity decides this process gets to freeze and then this process gets to run. So the outside entity gets to decide which process gets allocated to the CPU and when. The process isn't aware of the fact that it gets swapped in and swapped out. It just gets frozen and unfrozen. Okay? So this is preemptive context switching. This is the line item that you will put on your resume as a result of this class, and employers will think, you did what? Because we are implementing a preemptive real-time operating system. And that's no small task. You'll agree with me on that one at the end of the semester, I'm sure. Okay, so we are also implementing a cooperative context switch. So our context switch will be able to be used both cooperatively and preemptively. So we will support both the preemptive and cooperative. So now back to question one, which is the much harder of the two. How do you implement context switch? Well, okay, it's pretty much 3 steps. Push all the registers onto the stack, switch the stack pointer register to point at the new process stack, and then pop all the saved register values into the registers. Straightforward enough. This will get a little bit more complicated because we have to look at this in assembly. And it'll get a whole lot more complicated when we look at the implication of doing this preemptively. Okay, CS, context switch. This is a function you call in C. So this is a function we're going to implement. It's implemented in assembly, but we are going to call it from C. So its prototype is void CS. It takes a pointer to an unsigned int, and it takes another pointer to an unsigned int. Okay? So don't be fooled by the fact that this is a pointer to an unsigned int. That's just saying we've got a pointer to a memory location that holds the context of a process. So B is a pointer to the process's stack that we're going to swap in. A refers to a memory location where we are going to put a pointer to the old process. So we're going to take the current stack, the process that's currently running, we're going to swap it out. So we're going to take the context of the process that's currently running, save it onto the current stack, and then we're going to remember where the top of the stack, of that stack where we saved all that information is. We're going to remember that by writing it into a memory location pointed to by A. So this often scares the tar out of people because, wait, you've got another star there. I have trouble enough with pointers. You know, you're giving me a pointer to a pointer. Well, don't worry about it. It's just a pointer to a location where we're going to put the top of the stack. Okay? So this is where we're going to put the old stack. This is where we're going to copy the pointer to the top of the old stack. This is the pointer to the new stack, where the context of the process we're swapping in is located. Okay? Why the second level of indirection? Okay? Because what we're dealing with here is pointers to a stack. We're assuming that our stack is a stack of 4-byte values, and so we're abstracting it or thinking about it as a bunch of unsigned ints, even though they're not a bunch of unsigned ints. So the top of the stack, so the stack pointer itself, the data type of the stack pointer in this context of what we're talking about here, we're saying is an unsigned int star. Okay? So if we're going to write a pointer to an unsigned int to a memory location, then we have to pass the address of a location where we can put a pointer of unsigned int. So in order to pass the address of or a pointer to a memory location that can hold an unsigned int pointer, you have to pass a pointer to an unsigned int. Clear as mud? Did that help at all? Yeah. That was probably worse. Other questions? Okay. So, the other way of thinking about it is we're going to pass two variables to context switch. The second one that we pass is a pointer to the new stack. The first one that we pass is a location where we're going to remember where we put the old stack. Okay? So if we want to, and just like in all things with C, if you want to pass a memory, if you want to pass an object that you want a function to write to, you have to pass the address of that object. So this is how we would write an invocation of CS where we want to switch from the process that's currently running to a process whose stack is pointed to by P1 stack. So what we're going to do is we've got these two pointer variables, P1 stack and P0 stack. P1 stack points to a stack where the context of the new process is stored. P0 stack is just a pointer variable. Okay? We are going to store in that pointer variable the location of where we wind up the current process's stack. So we pass the address of P0 stack, and then we pass by value P1 stack. Okay? So we're going to look at a couple of stack frames to see exactly what this is doing. So we can declare two variables here, unsigned int star P0 stack, unsigned int star P1 stack. We can write a function, swap 0 to 1, void, and that just calls CS, passes the address of P0 stack, and then the value of P1 stack. Before we can invoke that, we have to have the following situation. P1 stack, we don't care what it points to. We're going to overwrite this value. P1 stack is a pointer to a stack. What we mean by that is it's got P1 stack, and it's got P1's context. The contents of its register file are saved on the top of its stack. So it's just a pointer to the top of a stack. This is what the P1's process 1 stack frame looked like when we swapped it out. Okay? So what exactly does it look like? Well, as soon as we dig through the context switch code, we'll show you how the stack frame is built up when we swap a process out, and you'll see all the gory details. But this is just, we suppose that we have, that P1 was running at one point. We decided to swap it out. So we stored all of its context at the top of its stack. By the time that we were done, the stack pointer was pointing to the top of the stack. We knew that we needed to use the stack pointer register to point at the new process. So we just remembered where that stack pointer was pointing by pointing P1 stack variable to that location. So this is what P1 stack looks like at the point that we are now ready to swap it back in. P0 stack doesn't point to anything, or it points to, it can contain some garbage value, but we're going to write to this variable. We're going to save P0's context to P0's stack, and then after we're done saving it to its stack, we're going to copy the current stack pointer register into that location, into P0 stack. That way P0 stack will point at the top of P0 stack, indicating where its context is saved to. So when we start, it looks like this. P0 stack points to we don't care. P1 stack points to process 1's context and stack. When we're done with the call to CS, P0 stack now points to this is the stack of the process that was running before we called CS. P0's context is stored at the top of that stack. The P0 stack variable points to the top of that context. P1 stack points to some location. We don't care, because what happens now is the stack pointer register is now pointing at the top of P1 stack data. We've taken the P1 context data that was at the top of that stack, we've taken it off of that stack, and we've copied it into the registers. So the context information is now swapped into the processor. The stack pointer is pointing at the top of the stack. We're ready to start executing P1. So effectively what will happen is we'll execute a return instruction, and that'll cause P1 to return back to wherever it was before we swapped it out. So we now have the before and after shot. Okay? Later on, if we wanted to reverse this process and we wanted to swap P1 out and swap P0 in, we would just call CS and pass the address of P1 stack, and we pass by value P0 stack. So what this does is it will save the context of P1 onto P1 stack. It'll point the P1 stack variable at the top of that memory location where we saved that information. It will then point the stack pointer to wherever P0 stack points, unload the context, and execute in the context of P0 now. Okay? So this is how you switch from P1 back to P0. Okay. So what we've seen is what is a context? We've seen the idea of having a C function that we call, that we save and restore context, and we've seen the before and the after shot from this. So now you got to massage your brain into ready mode here, because this we're going to be talking about a bunch of chunking assembly code, and it's going to be today won't be too bad. Next time's nasty, and the time after that's really, really nasty. Okay, and if you don't get this stuff, you're not going to have any chance. Okay, so we're going to have to push and pop a lot of registers. Just so happens that ARM assembly has a nice couple of instructions that help us out with pushing and popping a lot of registers. We have the STMFD instruction. ST means store, M means multiple, FD means full descending. So you remember how I said that the stack pointer points the last thing you pushed? ARM lets you control that. You can decide that I want my stack pointer to point at the last thing I popped. Or you can decide I want it to, and you can say I want stacks to grow instead of from low addresses to, or from high addresses to low addresses. You can decide I want it to grow from low addresses to high addresses. And you use different variants of the STM function in order to do that. So by convention, we are sticking with the same stack convention that you learned under x86. So we are storing in full descending mode. So what that means is the stack pointer points at the location in the last location that you pushed something. Descending means when you're going to push something else, you go from the current address to a lower address because you're descending from high addresses to low addresses. Okay. The other trick is that we don't care what register you use for a stack pointer. So there isn't anything magical. So we're doing an STMFD to push a set of registers, and we'll push them all onto the stack. But you can use an STMFD and an LDMFD, which is the opposite instruction, to store multiple registers to some location in memory, where the register that you pass to it as the address register just says, this is a pointer to where I want you to store this. Store a bunch of them as if you're pushing it on the stack. So this is an instruction that says, push a bunch of registers as if you're, so store a bunch of registers like you're pushing it onto a stack. But you don't have to use SP as the location in memory where you're pushing them. You can use a different register if you want to. The other thing to realize is that we're going to give it a set of registers, and it decides which registers it's going to put. So this note right here, PA5 through 48, this is in the ARM reference manual, and that will be something you'll want to look up when you're doing Lab 5. Okay? Basically what it's saying is we push the registers in a particular order. When you pass a set of registers to an STMFD, you store the lowest number register, and that's stored at the lowest address, and then you go on up from there. Mitch.
Why didn't you use this for the ISR code?
Why didn't we use this for the ISR code? Because one step at a time. You know, I could show you the STMFD code, and that's real slick and all, but that ISR code is going to blow up in our face here in a bit. So, okay. So STMFD, the opposite of the STMFD is the LDMFD. So that's load multiple full descending. What that means is load a sequence of registers as if they were stored using an STMFD instruction. Okay. Then we also have the MRS. Note, this is not BYU. That is not the name of a degree. What this is move the contents of a general purpose register into the CPSR. MSR, move the contents of CPSR into a general purpose register. So you have to have special instructions that you use to interact with the CPSR register. Okay? You can't just execute a move operation and access the status register. You have to use these two instructions. Those are privileged instructions. User mode cannot access those instructions, but we are executing in a privileged mode, so we can. Okay. Next thing to remember before we dig into this assembly, stack pointer points to the top of the old process stack. R0, so this is an assembly implementation of a function. We pass two parameters, A and B, leftmost, rightmost parameter, okay? R0 contains A. That's the address of where we're going to store the top of the old stack. R1 contains B. That's the top of the new stack. Both of those are pointers. So we're going to write to the memory location pointed to by A. We're going to read the memory location B. Okay, so those guys, A's in R0, B's in R1. All right, the moment we've all been waiting for. Here's the context switch code. Yay. Okay, got it? You understand? Good. All right, we'll go. Okay, so we start by pushing all the registers. So we execute an STMFD and we pass it ST bang. Note that is not exclamation point. That is bang. That's left over from the old user or the old Unix days. An exclamation point is pronounced bang. So ST bang. What the bang means is that we're going to store starting at the address indicated by SP, and we're going to store a bunch of stuff. And we're going to, as we store, we're going to have to increment and calculate the next address of where we're going to store the next register. So we're going to store R0, R1, R2, up through R10, then FP, SP, LR, and PC. All those guys are registers in the register file, the ARM. So we're going to store each one of those guys. We're going to start at the address SP. When we're done, we're going to update SP with the address of the last value that we stored. Okay? So what this bang says is when you're done, make SP point at the last thing you stored. So this is effectively a push. Yeah.
So SP is pointing at something already, right?
SP is our stack pointer. That's our stack pointer register, so it had better be pointing at something already. Yeah. So it's pointing at a location in memory. This is just basically push all these registers onto the stack, make the SP point at the top of that stack when you're done. Okay? The bang is necessary because this STMFD is a very flexible instruction. You don't have to move the stack pointer register to point at the top of the stack, but then again, we wouldn't be a valid stack if we didn't do that. So you have to have the bang if you're using this to act like a push. Okay? So the next step is we push the CPSR. You remember we have to have the CPSR register as part of the context of the process because it's got the condition codes in it. So in order to push the CPSR, you can't just push the CPSR register directly. There's only the two instructions that we can access the CPSR, the MRS and the MSR. So we're going to execute MRS to take the contents of the CPSR and put those into R2. The next thing you have to be paying attention to with ARM assembly is it's not like the GNU x86. Typically, we have the destination register first, and then the source registers. Okay? So we're moving the contents of CPSR into R2. Then the next instruction, store R2 into this blah, blah, blah. So what the blah, blah, blah says is take SP, subtract 4 from it, and take the contents of R2 and write it to that decremented memory location. Then we have the bang on the end of the addressing mode. What the bang says is update SP to the decremented address. So this is another way of doing a push, but this is how you do a push with a single register. So we saw this syntax when we were looking at the CSR's code. Okay, so this just says push R2 onto the stack, update the stack pointer to wherever you were before, or to wherever you ended up. Right. So it'll update after. So this says copy R2 into the location SP-4, and then write into SP-4. All right. Next is we have copy R0. All right. Remember, R0 is it's A. This is the location. It's the pointer to a location of where we want to store the top of the pushed stack. The top of the. So what we've done here is we've pushed all the registers in the CPSR. For the time being, that's our context. Okay. So we've pushed all that, and the stack pointer is pointing to a stack that looks like that now. And what we want to do is now store the top of that, a copy of that, where the stack pointer points, into wherever the parameter that we were first passed points. So we're going to take SP, which is the pointer to the top of the stack. It's currently pointing at the CPSR we just pushed onto the stack. We're going to take the pointer, SP, and store it at the memory location R0 plus 0. So R0 is the pointer to the location of where we want to store the top of the stack, and this stores the top of the stack at that location. So copy SP to star R0 plus 0. Okay? So now we've saved where we put the old process's context. Now we need to focus on loading the new process. So loading the new process, if you remember, the second parameter that we passed, which is passed in R1, R1 points to the new process's context. What does that new process's context look like? Just like the old process's context, except for with different numbers in different places. So it's the same format. The top of the stack will be the CPSR, followed by all the registers that were pushed on with an STMFD, followed by the rest of the stack for the process we're swapping in. So the first thing that we're going to do is we're going to restore the new process's CPSR register. So we do that with this LDR. This is a load. It says load into R2 the contents of memory pointed to by R1. And then what we're going to do with this #4 after the end, that says take R1, add 4 to it, and put that value back in R1. So this is kind of like the bang, but because we're using this post-increment notation, the bang would be redundant. So this says R1 contains an address, so load from that address into R2, add 4 to R1, and update R1 with with the new address. Mitch.
Would it be the same thing if we do R1, #4 bang?
So would it be the same thing if we had R1, #4 all inside the brackets? The subtle difference with that would be we want to fetch from the memory location pointed to by R1, not R1 plus 4. So this is a post increment, whereas the other one, this guy up here on this on 2, where we're storing R2 into SP, #4, that's a pre-increment. So we want to grab from R1 and then update R1. So what this is doing is it's grabbing the first location that's on the top of the R1 stack. So we're treating the new processor stack as if it were a stack, but we're using R1 kind of like a stack pointer. So this is a pop, okay? But we're not using SP here. We're using R1 instead of SP. Okay, so we pop the first guy off of the stack pointed to by R1. Then we move the value that we grabbed off of that top of the stack into the CPSR register. Okay, so that moves contents of R2 into CPSR. So that restores the CPSR from wherever it was for when we swapped out process 1. Okay, now R1 is pointing to all the registers that were on P1 stack. So what we need to do is we need to restore that context. The way that we do that, first what we want to do is just say, okay, we're gonna now treat this as a real stack by pointing the stack pointer at it. So we move the contents of R1 into SP. So now that points SP at wherever R1 was pointing to, which is the top of the P1 process's stack where all the registers are stored. And now we execute an LDMFD. So this pops all the registers. So we pass SP. Note there is no bang here, and that is significant. And I'll explain why in a second. But we take the top of the top of P1 stack. We're going to load R0, SP, SP, and PC all from that stack. Okay? So that pops all the registers and restores P1's context, and that also implicitly does a return operation. It causes us to jump back to wherever P1 was executing before we executed the context switch. Mitch.
When you first LR was in there, and now you're popping it back.
Okay, so yeah, I have a subtle little trick there. So if you and I have that documented in our discussion. So if you look up here at the top of this guy, we pushed R0 through R10, SP, SP, LR, PC. Down here we pushed R0 through R10, which is matches there, SP, SP, PC, SP, SP, LR, PC. Okay, so we pushed an extra register that we aren't popping, or at least we're seemingly not popping here. LR is the link register. Okay, so what we use this for, whenever you call a function inside x86, you push the return address on the stack and jump. Whenever you call a function inside ARM, you copy the return address into LR and jump. Okay, so in order to think about this properly, you have to think about P1 was swapped out with this code. It is not the function, it's not the process that's being swapped out as it's being swapped in. So one invocation sometime earlier, we swapped out P1. Now we're swapping it back in. When we swapped out P1, the LR register contained the return address of that function to wherever P1 was running before we called the context switch. So this has the return address of where P1 was. We'll push that onto the stack. Now we're going to, now on the second call to context switch, where we're restoring the context of P1, what we're doing is, when we pop these registers, we're popping FP into FP. So FP, we're popping into the FP register the saved FP value. We're popping into SP the saved SP value. We're popping into PC the saved LR value. Okay? So what this is doing is it's copying the return address into the program counter and causing us to do a return. Okay? So this is an indirect return instruction. So we're just taking the LR and putting it into the PC. Now, how come we only have to push these registers, but we pushed more registers than we're popping? How we get away with that is when we do the STMFD, we push SP as it existed before we executed the STMFD instruction. So we push a copy of the stack pointer as it was when we first start the call to CS. By popping SP into SP, we're restoring the stack pointer to wherever it was before we called the STMFD. So that implicitly pops that last register off. Are there different ways you can do this? Absolutely. So now that I've explained this in painstaking detail, what I'm going to do is repeat myself and explain it again in painstaking detail because this is so important. Okay? So if you see 1, 2, 3, 4, 5, 6, those 6 groups of instructions, what I've done in the notes is documented each step, what's going on with them. Okay, so in step 1, well, prior to step 1, A is a pointer to where we want to store the old stack, and it's passed in R0. So R0 is a pointer to a memory location. It's not a garbage pointer. Its contents could be garbage, but R0 points to an allocated, well-defined memory location that has some information in it that we don't care about. We're going to overwrite the contents of the box that R0 points to. Okay? So this is what the stack currently looks like. So P0 is currently running. It's got stuff on its stack, return addresses, saved information, local variables, context, call stack, whatever. It's got a bunch of stuff, and the stack pointer is pointed to the top of the stack. So this is what the machine is doing before we start executing. So step number 1, push all the registers onto the stack, pointer to by SP. This is the old processes stack. So the stack pointer was pointing down here. We've now put R0 through R10, R11, R13, R14, R15. And now you say, wait a minute, I didn't see any business about R11, R13, R14, R15. Okay, here's the dirty, nasty little secret. Okay, R15 is the program counter. R14 is the link register. R13 is the stack pointer. R11 is the other guy that I can't remember which one it is. It was the FP, frame pointer. So these are, you can use those guys interchangeably. R11 could be you can either in your assembly code say FP, or you can say R11. Doesn't matter. They're syntactically the same thing. Yeah.
Does it matter which order it pushes the registers?
You can write. So the question is, does it matter what order the registers? As I cut you off and didn't let you finish your instruction, your question. Anyway, it doesn't matter what order you write the registers in the STMFD, LDMFD. The assembler will reorganize them, and you'll end up pushing them in the order of lowest numbered register to lowest address. So just remember, you're pushing these onto the stack. The lowest address is at the top. So R0, R1, R2, R3, and so forth. Even though typically we think about R0 would get pushed on first and R1, so intuitively you'd think it's backwards here. But the hardware dictates that lowest number register gets pushed at the lowest address. And you'll need that piece of information for Lab 5. Okay, step 2, pushing the CPSR. So all that we're doing there is just copying the CPSR register on top of the stack. So we pushed all the registers onto the stack, then we copied the P0 CPSR. Stack pointers pointing to the CPSR. Step 3, save the top of the old process stack. So that just says write to, you remember how we had the write to the bracket R0, 0? So what we're doing is we're copying into the box that R0 points to, we're pointing that to whatever the stack pointer points to. So we're just saying that wherever R0 points to, that's a pointer. It points up there to the top of the stack. So this guy points to wherever SP is pointing to. And now what we're going to do is we're going to forget about this. We're going to erase the stack pointer. The SP register will no longer point to here. The reason why we do this is so we can remember where the top of this stack is so we can later restore it. Okay, so we have to remember that part. Step 4, this is where we start restoring the new process's context. The second parameter B, which is contained in R1, is a pointer to a context of a stack, and it's in the same format as the old stack. So it's the P1 CPSR, P1's copies of R0 through R10, R11, R13, R14, R15, and so forth, and then P1's data on its stack. Okay, so this is in the same format, but its register values are specific to P1. Okay, so the CPSR is at the same location on the P1 stack as it is on the P0 stack, but it's got different values because this is process 1 stack. Okay, so for step 4, we treat R1 as a stack pointer, and we're going to pop from it into R2. We copy R2 into CPSR, and then that puts and then we'll put R1 at R1 plus 4. So what that does is it just moves CPSR, the saved CPSR value from the R1 stack into the CPSR register, and now R1 points at the top of this location where we've got P1 registers. And then step 5 is point the SP register at what R1 points to, so that just takes SP, the register, and points it at this location, and then we do the LDMFD, which pops all those guys off the stack. Okay, and this is where that discussion is, where if you note here we had STMFD, SP bang, all the registers, LDMFD, SP no bang, and these registers. Where's the LR in this guy? Again, that's because I'm popping from the location where I pushed LR onto the stack, I'm popping that into PC. So that causes me to do a return. From the location of where I pushed SP, I'm popping that into SP. So I don't need to have this instruction calculate what the SP should be, because I'm already going to remember what it was when I first started the STMFD. When I stored it, I remembered what the stack pointer was. I'm restoring the stack pointer to what it was prior to doing the STMFD, so I don't need to have the bang on the SP in the LDMFD. So that discussion just summarizes that. Okay, questions about context switching? Yeah, here. Yeah, so the hardware will guarantee you that it will put R0, if you're doing an STMFD and you have R0 in the works, R0 will be pushed to the lowest address of the set of addresses that it pushes to.
Now with the LDMFD, is that specific, like it pushes those?
The way you think about an LDMFD is it just undoes what an STMFD does with the same stuff. Okay? So it just does it backwards. So when you're thinking about full descending in the context of a load, doesn't make a whole lot of sense. You got to think about it. It's just undoing what an STMFD does, and it assumes that the registers are in the format in the order that an STMFD with a similar parameter would store them. Okay.
Well, if we were to like change this, SP or the PC or whatever in the LDMFD, would that change for the sum of that? Is it like 1-to-1?
Hand it to me again.
We don't say R0 to R10 initially. If we put like PC first, is that going to push R0 onto the program?
Okay, so if you say PC, comma R0 to R10, it doesn't matter because it says you want me to load R0, so I'm going to assume that that's stored at the lowest address of the range of addresses that I'm provided. Okay, other questions? Mitch?
So we're assuming that the process already knew that it was being preempted when we invoked this function.
Okay, so the question is, are we assuming that the process knew it was being preempted when we did this function? And this function is for cooperative context switching. So this would be for when a process actually invokes the CS function call directly. Okay. In order to actually make it work with preemptive, we got to complicate things a little bit more. And to make it work for both cooperative and preemptive, it's bad. It's going to take about 100 lines. We're going to make the ISR's code into about 100 lines of code, and we're going to make that guy we're going to probably double or triple the size of the context switch code. And it's all about what mode am I in. Okay?
I'm sure you're going to talk about this, but I just can't focus until I at least have this.
You're just stalling so I don't go on to the next set of slides.
Maybe.
That's okay.
Whatever the top controller guy is,
yeah.
he's got to be running And so do we save his context when, or are there like special registers that we're not touching?
Okay, so we've talked about the magical controller entity that could decide who gets to swap back and forth between process 0 and process 1 and who gets to swap them back and forth. So does that guy, the magical controller entity itself, have a context, and do we need to save its context and so forth? I will say yes indirectly, and we will do all of that, and I'll show you how it's done, but you're already doing some of that to some extent. Okay, successful stall, all quit. We don't stall anymore. Now we'll just call it a context switch. So you're going to have to save this context in your brain and reload it come Wednesday. Remember, big capacitors, small resistors.
Yeah.